Hi guys, how's it going? So today actually we're gonna go through the RCNN family models. Um, I think this will be a two-video series whereby in the next video we're going to build it from scratch. However, I have to say that the mask RCNN is quite complex. I've kind of like went through the source code of the model and it has like over like 3,000 lines of code. So there's quite a lot of stuff involved. So, but I think it'll be good to code the smaller version of the model, mainly because it's just for us to understand how it works from the code perspective. So today I thought it would be a good idea to kind of walk you through all the RCNN family models so that you can appreciate all the advances that have been made and you can also see how they work internally. RCNN is also known as a region-based convolutional neural network. This was the first model in the family of RCNN, and it was based on two main ideas, which was that we're going to have a selective search and a convolutional neural network. The selective search purpose is to identify manageable number of bounding blocks, whereas with the CNN, we try to extract features from those regions independently. Looking at this from a visual perspective, let's say we have an image, right? And we want to identify an object in that image, or classify that object, an object in that image. What we're going to do is that we're going to pass this image towards the first component, which is called extract region proposal. So this is where the selective search algorithm take play. What it does, it tries to propose multiple regions of interest. So in the paper, they said, I think 200,000 of regions are being proposed. Then what we do is that we take those proposed regions. By regions, I mean all the possible objects that could be there, right? They're then grouped to have a fixed size, mainly because we have to pass this in the CNN. What we do is that the CNN, before we explain what it does, is that it's a pre-trained model based on like image classification. This could be ResNet, or it could be VGG or something like that, right? So what it does is that we have to fine tune all the proposed regions for K+1 classes, okay? Then the CNN is going to generate the feature map, the feature vectors for every regions that we have proposed. So you can think here we have multiple CNN. So each CNN take a region, each CNN take a region, each CNN take a region, each CNN then propose a feature vector. So each CNN then we take that feature vector, we push it towards a support vector machine. We take this, we push it towards support vector machine, and this is a binary support vector machine which is trained on each class independently. Then the final step is that because of we have bounding boxes that have been predicted on the object, what we do is that we need a way to be able to calculate how off we are in terms of these bounding blocks. A regression model is trained to correct the detection window on the bounding blocks, so we use the localization error to take care of this. We call this bounding box regression. So for instance, let's say we have the predicted bounding box, right, denoted by PY and PX as is going to be our center coordinates, and PH and PW is going to be our height and width. Then we have also the ground truth, which is GY, GX, and GH, and GW. So what we do is that we configure the regression to learn the scale invariant transformation between the center, right? Then we apply also the log scale between height, and width. Now, these are going to produce a score, a confidence score. So, with that, therefore, I think there will be multiple bounding boxes that have been proposed for an object. So, for instance, if you have a person, there's going to be a bounding box proposed, going to be bounding box proposed, going to be bounding box proposed. So, I want to talk about the common tricks that we use to make sure that we have an accurate bounding box, right? So we use what we call a non-maximum suppression. Non-maximum suppression. So what it helps us to do is that it helps us avoid repeated detection on the same instance. Help us avoid repeated detection on same instance. So it does this by, firstly, it's going to sort the bounding box by confidence score, right? So it bounds, then it tries to discard low confidence score. Discard low confidence scores. So if the bounding box remains for a single object, a greedy algorithm is used to select the highest score of this. So that's how we end up with one. And like we said in the diagram, that we propose multiple regions and we pass them through a CNN, but some of the bounding box could have been we could have proposed multiple bounding boxes. So this is the technique that we use. It helps us to make sure that we select the best proposed bounding box. So that was RCNN, but the model suffers a lot. So what are the things that it suffers a lot from? So firstly, we know that the selective search algorithm has to propose like 200k, right, regions for every image. This is very, very expensive. This is very expensive, right? So the second component that we need to consider is that we pass each of these regions to CNN, right? So you can end up thinking that we have like 2,000 CNNs, which have to produce a feature map. So this is also quite expensive. Feature vector, right? The third thing that we could have realized is that then each object has a trained SV classifier, right? So it's really hard to have a real-time object detection with this model, mainly because it can be quite slow. So we're going to take a look at the first RCNN and see how it tried to improve from these bottlenecks. So let's look at the improved version of RCNN bottleneck, right? So instead of extracting the CNN features for all the proposed region, what first the RCNN tries to do is that it tries to aggregate them into one CNN forward pass. So just a refresher, we said that we take all the regions, right, that have been proposed by the selective search, and we said that it's 2k plus 1, then we're going to be passed to each CNN, which would then produce a feature vector, But this time we're saying that we're going to take these 200k proposed regions, and we're going to pass them throughout a single CNN, which will then try to aggregate them into one CNN. So how it works is that we have a pre-trained model like ResNet, right? It has been pre-trained on image classification. Then we use them. The proposed region is still, the selective search algorithm is still there, which is going to propose the 200k regions. Then those regions will be passed into a single CNN network. Then we replace the max pooling layer with what we call our region of interest pooling layer, which we're going to discuss now, right? The region of interest pooling layer outputs a fixed length of region proposal, right? Then we integrate them with our softmax along with our box regression. So essentially you can think like we have the localization and the classification objectives. Okay, how is it able to do it? How are we able to take all of the proposed regions and pass them only through a single CNN? That's because we introduced this concept here now called region of interest. So it uses a single feature map for all the proposed regions. So what it does is that it outputs a fixed size feature map from non-uniform inputs by doing a max pooling. So region of interest essentially it tried to extract all the regions from feature map into a fixed dimensional map, something like that. So that's what it does. Then this will be passed in the subsequent layers. To solidify our understanding, let's look at an image. So if you can think like we have input image, what we do is that we pass this throughout the CNN. So what we'll do, the CNN or the convert it'll then produce region of interest. Alright, so these are region of interest, right, from a feature map. Then we need to extract these. We use region of interest pooling layer, right? So we extract these into fixed size. All of them have the same size. We push this into a fully connected layer, right? Then for us to calculate how off in terms of the bounding box, right? So remember the bounding box, we need to calculate how off we are, and we need to kind of like select the best bounding box. We trained a linear regression model. Then we have a softmax for classifying if like this object is a person or maybe some sort of like an animal or something like that, right? But I hope this image hopefully like solidify your understanding of like what region of interest pooling layer does. So we produce a feature map along with those regions that are on the feature map, right? Then the region of interest, using also I think max pooling, it tries to then take out those region of interest and convert them to be into a more of a fixed size. Then we post them into a fully connected. So that's how it works. So now let's look at the faster RCNN. So now looking at the faster RCNN. So in the first family of RCNN models, which was RCNN, we said that the selective algorithm, which was the algorithm that proposed the regions, was quite expensive. So the author, what they did now was to try to integrate the region proposal algorithm into the CNN model. So now you can think of faster RCNN as a unification of region proposal network along with the convolutional neural layers. So how it works is that essentially just focus on this portion for now. So what it works is that we have an image, right? We pass our image into the CNN, a single CNN. Then we have this thing called region proposal network. So it's a feature map, right? And then it made proposal about specific object in the image, right? Then we have region of interest pooling to take all of those proposed regions from there, right? So how does this uh, 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 region proposal network work? So let's scroll down and see. So if we take a look at this layer, so this is that how the original proposal work. So you can think of like it takes the input as the feature map. So the outcome of the CNN model, its feature map, then it's gonna take those feature map as input. So the region proposal network, it's also a pre-trained image classifier. So what it does is that it slide a small n by n special window right over the feature map. So at the center of the sliding window, we then predict multiple um, various scale, or we call them anchor boxes. So these anchor boxes essentially just to make sure that maybe if the image has multiple boxes that can fit their specific object. So now we are looking at the last model of the RCNN family, which is the mask RCNN. So essentially the mask RCNN extend the fast RCNN to a pixel level image segmentation. So it add this instant segmentation component. So this branch essentially is responsible for predicting an object mask in parallel. So this mask essentially is a small fully connected network applied to each region of interest in a pixel to pixel manner. So I think the most important thing that we should talk about is this region of interest align. So these layers here are the same with the first INN, the first RCNN. So I thought the different thing or the most important thing that they added in the mask was the region of interest align. So you can think of this as it was integrated because of now we're working with the segmentation. So we want to fix the localization misalignment caused by the quantization in the region of interest pooling. So this region of interest causes data loss. So how does it do it is that if you take an input image and you take the feature map, you will see that the specific region of the input does not align well with the specific region of the feature map. So the region of interest align. So it tries to map the region of interest accurately from the original image to the onto the feature map without rounding the integers. So it uses this bilinear interpolation in order to compute the floating point values in the input. But the point here is that if we have an image, right, this pixel here will accurately point to this feature map. So now we have these floating point representing these numbers. Hence we're using this bilinear interpolation. Now, because of mask was meant to work on a segmentation problems, so we have three loss functions, which is the classification, localization, and the segmentation. So that's all, guys. I hope this was helpful to kind of like introduce you guys to the RCNN family models. Yeah, I think probably in the second video I'll try to create code a small vision of the mask RCNN. And yeah, thanks guys for tuning in. Thanks, bye.